Hi, I'm Nicholas Dwork, and in this lecture we're going to be discussing functions. A function is a mathematical machine. Something goes in, the function grinds on that thing, and outputs another thing. Here's an example. The function is f of x is equal to 2x plus 1. In this case, if we input 3, it outputs 7. If we input 0, it outputs 1. If we input pi, it outputs 2 pi plus 1. We input these things on the left, and the function outputs these things on the right. So a function is a mapping from its inputs to its outputs. Rigorously, a function is a set, an ordered triple. So a function has a name, in this case f, and then it has 3 elements in the order triple, right? The first is the set D, which we call the domain. The second is the set R, which we call the range. And then there's this set S. What is S? S is a set of ordered pairs that assigns an output to each possible input. So it's a subset of the Cartesian cross product of the domain with the range. And for any element in the domain, there exists an ordered pair xy in S. And the y is the output that corresponds to the input x. So here's that example again. In this case, the function f maps the real numbers to the real numbers, and S is the set of ordered pairs. Here are some of those ordered pairs: 3, 7, 0, 1, pi, 2 pi plus 1. But this set S is infinite in this case. There's one ordered pair for every real number. Other ways we could specify this function, we could say the function f maps the real numbers to the real numbers. In this case, the colon reads as maps. So the function f maps the real numbers to the real numbers such that f of x is equal to 2x plus 1, and it's implied that it equals 2x plus 1 for all elements in the domain. Alternatively, we could say that under f, x maps to 2x plus 1, and in this case, the domain and range must either be inferred from context or specified elsewhere. Functions don't need to work on just numbers. We can have functions work on all sorts of things. In this case, we have a domain that consists of A8, star, and happy face. We have a range that consists of circle, square, and the number 5. And then we have this mapping S. And so S maps A to circle, 8 to 5, star to circle, and smiley to 5. Consider a function f with domain D, range R, and pairings S. The image of f is the set of all possible outputs. Rigorously, it's defined as the set of all y in the range such that there exists a pair xy belonging to S. And the image is, of course, a subset of the range. So if this oval on the left represents the domain and this oval on the right represents the range, and we see that all elements in the domain map to this subset of the range, then that subset is the image of f. Here is our example from before. We see that none of the inputs map to the element of the range square, and the image of f is just circle and 5. Here's another example. F maps the real numbers to the real numbers such that f of x is equal to x squared. We could plot this, and when we plot it, it becomes obvious that the image of f is the non-negative real numbers. That is the set of all possible outputs. Consider a function f like before. The preimage of a set B under f is the set of inputs that yield an output in B. It's denoted with this superscript -1. When you see f raised to the superscript -1 of a set B, that is the preimage, and it's defined rigorously as the set of all A and D such that f of A is an element of B. Like before, this is the domain on the left and the range on the right. Let's say this is the subset of the range that we're interested in. We want a preimage of B, and we see that these two ovals are the subset of the domain that map to that rectangle on the right. Then the union of those two ovals would be the preimage of B. Definition: the identity function I maps the domain to itself such that I of x is equal to x for all x in the domain. The composition of two functions, g and f, where the domain and range of g is b and c, and the domain and range of f is a and b, is g composed with f, which will have a domain a and a range c, where g composed with f of x is equal to g of f of x for all x in a. What does all this mean? Here the domain and range of f maps A to B, great. Then G maps from B to C, great. G composed with f just maps from A directly to C, as though you applied f and then applied G. And now we get to a very nice property of functions. It is really very nice when we have this, the inverse. The inverse of a function f that maps a domain to a range is the function f inverse. Now this -1 is read f inverse. The f inverse maps the range to the domain, where f composed with f inverse is the identity function, and f inverse composed with f is the identity function. So if f maps this point in A to that point in B, f inverse maps it right back. Only some functions are invertible. It's a very nice property. And in fact, a lot of engineering is trying to figure out what was the input that yielded this particular output. And so if a function is invertible, it's really nice because we just take the output, put it into the inverse function, and see what the input was. We don't always have that luxury. A real quick note here. Now we see that preimage and inverse both have the same notation, the superscript -1. So you have to be careful. If you're saying f superscript -1 of a set, well, that's the preimage. If you're saying f inverse -1 of an element, well, now you're passing an element into the inverse function. Okay, let's talk about some more properties of functions. Here's a definition. A function f that maps the domain D to range R is onto means the image of f is equal to the range. This is also called surjective. So what is onto or surjective? It means that you can get to every element of the range. There's at least one input for each element of the range. Separate definition, a function f is 1-to-1 means that if f of x1 is equal to f of x2, then that implies x1 is equal to x2. That is, if the outputs are different, then the inputs must be different. So here's an example where both x1 and x2 map to the same element of the range, so this function is not 1-to-1. A function that is both 1-to-1 and onto is called a bijection, and it turns out a function is invertible if and only if it is a bijection. So one way to prove that a function is invertible without necessarily finding the inverse function is to show that the function is both 1-to-1 and onto. So here's an example. It's the same example as before. We can plot this, and we see that there is an input for every possible output. So it is onto. Each input maps to a different output, so it's 1-to-1. Therefore, it's invertible. And in fact, we can go about finding the inverse. F of x is equal to 2x plus 1 if and only if f of x minus 1 all over 2 is equal to x. So this gives us the inverse function. The inverse maps the real numbers to the real numbers such that f inverse of y is equal to y minus 1 all over 2. Two more examples. Here, f is the function that maps the non-negative numbers to the real numbers such that f of x is equal to the square root of x. We're plotting it on the right. And we see that this function is not onto, since there is no input where the square root of x is equal to -1. In fact, there's no input where the output is any negative number. I just chose -1 as a single counter example. Okay, so therefore this function is not invertible because it is not onto. Here's another example, a very related example. F maps the non-negative numbers to the non-negative numbers such that f of x is equal to the square root of x. Okay, well now this function is both 1-to-1 and onto. There is in fact an input that will get any positive number. So when the range is just the non-negative numbers, the function is onto. Since it's both 1-to-1 and onto, it is a bijection and therefore invertible. Here's a particular type of function. It's called a binary operation. A binary operation on a set A is a function that accepts elements from the Cartesian cross product of A with itself and maps to A. What does this mean? It takes two inputs, both from A, and it outputs to A. So what are examples? Addition and multiplication are both binary operations on the real numbers. Each of them takes two numbers and outputs one. It's a binary operation. Okay, here I'm going to denote a binary operation with the symbol square. So a binary operation square that maps A cross A to A is closed with respect to subset B of A, means that the same binary operation, when restricted to the domain B cross B, maps to B. So for example, addition on the real numbers is closed with respect to the non-negative numbers. If you add two non-negative numbers together, you get back a non-negative number. Therefore, it's closed with respect to the non-negative numbers. Since a function is just a set, there's nothing stopping us from having functions that accept and or return functions. We sometimes give these types of functions special names. So a functional is a function that accepts functions and returns a number. Or a functional could be a function that accepts elements of Rn, where n is greater than or equal to 2, and returns a number. Both of those types of functions are called functionals. And a system is a function that accepts functions and returns functions. So we're on our way to building a solid foundation. That'll do it for today. Thank you for your attention.